In this video we're going to be looking at the proof of centripetal acceleration. So we've looked at some of these questions already where we have maybe string with a tennis ball around it. The tennis ball is rotating around in a circle. Similarly, the moon could be rotating around the earth. The tension in the string for the tennis ball would be directed towards the center of the circle. So let's look at knowledge that we already have from the unit circle. From the unit circle we have any point on the unit circle if the angle inside is theta, and r is the radius, will be r cos theta in the I direction, or r cos theta, or sine theta in the j direction. So if we change this to radians, which is what we're working with here, after t seconds, if our angle is w, the angle opened up will be wt in radians, and r is still the radius. So similarly, the point on this unit circle, or my displacement on the unit circle, will be r cos wt in radians in the I direction plus r sine wt in radians in the j direction. And if we write our displacement formula out, what is s equal to? Ut plus a half at squared. We're looking to get to acceleration, don't forget. If we differentiate s with respect to t, or displacement with respect to time, we're going to get u plus twice a half, which is 1, so just u plus at, which is my velocity vector. And if I have my velocity vector is equal to u plus at, and I differentiate velocity with respect to time, you guys know this already, you're just going to get your acceleration. So that's what we have to do on this question. We have to take our displacement vector, which is r cos wt in the I direction plus r sine wt in the j direction. That's s. So displacement with respect to time, ds dt, is going to be equal to, you know, or if you don't, you do now, that cos goes to minus sine. So we're going to get minus r sine the angle, and then we differentiate the angle, and if we differentiate wt with respect to t, we get w. That's going to be in the I direction. And if we differentiate sine, we get cos, so this one becomes r cos wt in the j direction, but we have to multiply by the differentiated angle, which again is w. So tidying this up, bringing the w to the front, I'm going to get minus w r sine wt in the I direction plus w r cos wt in the j direction. So this is my velocity, and if I differentiate my velocity with respect to time, I'll get my acceleration. So again, sine goes to cos, so it's going to stay as a minus w r cos wt by the differentiated angle, which is w in the I direction. Cos goes to minus sine, so this is going to be minus w r sine wt by the differentiated angle again, which is w in the j direction. So a, which is equal to dv dt, becomes w and w minus w squared r cos wt in the I direction minus w squared r sine wt in the j direction. And if we look back at what we had originally for displacement, we had r cos wt. So if I factor out the r cos wt, you can see what's left is minus w squared, and that would make the middle sign a plus, or sine wt. I'll put in my vectors, my j and my I. So what have we got here? We have minus w squared by displacement. So you can see that the A is directed along S, but in the opposite direction. We were looking in this direction. Because of minus w squared, it's directed in this direction, which is towards the center of motion. So this is my w squared, my minus w squared S for my acceleration. What else do we know? Well, we know we can get the magnitude of A by using Pythagoras. So the square root of these two things squared, I'll take it from this line here. So the minus will go to a plus anyway, so it's going to be w to the power of 4 or squared. If I square both of these two things, and then it's going to be cos squared wt, and the I direction, and then in the j direction it's going to be the same. It's going to be, sorry, one up above, it's down below, w to the power of 4 or squared sine squared wt. And what do you guys all know about cos squared plus sine squared? You know that cos squared plus sine squared is equal to 1. So if I factor that out, I factor out my w to the power of 4 or squared is the product here, so I can create two brackets, and I have cos squared wt in the I direction plus sine squared wt in the j direction. I'm going to get the square root of w to the power of 4 or squared times 1, which is just w squared or. So this is the magnitude of my acceleration. Now, what were we asked to show? Going back to the start, we were asked to show A was equal to v squared over r. So we currently have w squared r, and from page 51 of the tables, we can use the information that's given. We know that the linear velocity is equal to the angular speed times the radius. So we want v in here, so I'm replacing w is equal to v over r from this formula. So we're going to get v over r squared times r, which is equal to v squared times r over r squared, which is equal to v squared over r. That is the proof of centripetal acceleration. Let's just have a look at the magnitude of the velocity, which should be wr. So we go back to our velocity from up above here and come to the right. The magnitude of this velocity is equal to, similar to what we've just done, squaring w and r, we're going to get w squared r squared, big long bracket, w squared r squared sine squared wt plus w squared r squared cos wt. I've left out my I and j, but you see where it's going. The magnitude of this velocity is going to be equal to the square root of w squared r squared by the square root of sine squared plus cos squared, or cos squared plus sine squared. So this is the square root of w squared r squared times 1, which is equal to wr. My v is equal to wr. And these are the two proofs that are required in this chapter. So get practicing, nice and easy, but you do need to know your rules for differentiating sine wt and cos wt.